Yeah, good afternoon, everybody. I'm very happy to see here so many people, and the rest of you are online. We have 124 people registered for this lecture, so I'm quite happy that you all are here, but for sure in presence is much better as online. Nevertheless, I also would like to greet our participants who are at home or at work in front of their monitors. And I'm really glad and really happy because today we have the first future lecture, and this is a new format for us, for TUHH. That is why I would like just to explain you shortly what we are going to expect and what is the purpose of this lecture. So as you know, recently we have restructured our research fields, and we have formulated 5 research fields in our university, which you see here. And one important research field for today is environmental and energy system, because this research field organizes this future lecture. But we have these 5 research fields, and they are very interdisciplinary. They have nothing to do with our School of Science or with our deans. Everybody can join who feels as a researcher that he can contribute something to that. And what we are looking at, especially now, what is the societal and economic impact of our research? So what we are doing in Hamburg, how does it impact our society? And in this sense, we would like also to show and to organize our research in a way which is beneficial for such a structure. And one element of our research is this future lecture, this new format. As I told, each research field organized once a future lecture, and today the head of the spokesperson of the research field in economic and energy and environmental system, Professor Ernst, took the advantage to organize the first lecture. And what we expect today, first of all, we expect a very exciting topic, and we expect also that this topic would motivate us to think what else and what new we can do in our research, how we can at TUHH maybe also do something in this field which we were not thinking about before. And that is why one of the purposes of this lecture was also a networking afterward. And to support this networking, we will have 4 posters here, which you see on the gallery, which are also connected a little bit with this topic and which fits very well to this topic. So we would like to have then the discussion also near these posters. We have here also our new professor presenting his poster, Professor Kulau, and we have also the poster of the other research field, and also some of the research posters which are really showing what we are doing at TUHH in this area. And so that this networking is not dry and boring. We have something to drink and some pretzels. They are outside near the exit, but I do hope that some of you still grabbing those, come back and have a look and have a nice discussion near the posters, also with our presenters, with the authors of the posters, and what is the most important, with each other, because we would like also to initiate and to engage you in this networking. So I do hope that that will also happen, but so that we have a topic and we have something to discuss, we have today our first future lecture, Will Hydrogen be the new climate neutral natural gas? And this is a question, and I hope we will have an answer, or maybe even more questions during this lecture. And Professor Ernst, as a spokesperson of the research field, would introduce our lecturer today. So please, Professor Ernst.
Thank you, and it's a great pleasure for me to present Professor Dr. Gerald Linke here for the first future lecture. Gerald Linke is CEO of the German Gas and Water Association, the national standard-setting body and R&D organization for gas and water. Prior to this position, he worked at E.ON as Senior Vice President Global Engineering and as managing director of KGNR, a grid operator for transport and Heightain in the industrial Ruhr area. Before 2011, Professor Linke served at different leading positions in the E.ON Ruhrgas group, such as Senior Vice President Research and Development and Director of the Northern German region, being responsible of several thousands of kilometers of high-pressure natural pipeline grid. Professor Linke is a graduate of mathematical physics of the Technical University of Braunschweig and has a doctorate degree in physics. In 2014, he has appointed honorary professor at the Ruhr University Bochum. Professor Linke is the German associate representative in the International Gas Union. From 2018 to 2020, he was the president of Gas, the technical and scientific EU association of the gas industry. Since June 22nd, 2020, he is the president of ERIC, European Research Institute of Gas and Energy Innovation. So we are happy to have you here. Welcome at TUHH. The floor is yours.
Thank you, Professor Ernst. Thank you, colleagues. It's a pleasure for me to be here and also as the first candidate for this future lectures. So if it goes well, please recommend me. If not, just see me as the first guinea pig and pick a new one afterwards. Yeah, before I start, just one slide about my association, German Gas and Water Association. We are the standard setting authority here in Germany, like DIN. Maybe some of you know the Deutsches Institut für Normung. We do this for gas, for water, and also for hydrogen. We run different labs and scientific corporations in Germany, and we are more or less involved into every hydrogen project and the big Reallabore here in Germany. And we are a non-profit organization where we train 40,000 people a year and also issue certification schemes, for example, here for hydrogen-ready components or other devices who are then safe and can be used, but also for hygienic reasons for water appliances too. Let me start with natural gas and some trivial aspects about natural gas before I have a closer light and a spot on hydrogen. Natural gas from a global perspective is seen as the natural energy carrier with the lowest emission compared to coal and oil, for example. So you have only half of the emissions for the power production if you compare it with coal and only 1/3 if you compare it with lignite. Natural gas has a tremendous share in our primary energy, which I will show in the next slide in more details, and it can be stored. And it's very important to have a molecule that stores energy, especially if you want to combine something with renewable power, which is fluctuating. It's also seen to be sustainable, and maybe you remember the news from last week where the European Parliament decided that nuclear power and natural gas are sustainable. Now, a lot of people criticize this and say only renewable power should be sustainable, but renewable power is already renewable, so that's already an attribute. I think it's right to talk about sustainability, as you will see during my presentation. What many people don't know is how our primary energy is composed. And these simple graphs, these squares, show you the picture of the world, of Europe and Germany. The whole square represents the entire primary energy demand. And the yellow part is the one that is delivered by natural gas. In the upper left, you can see the portion of renewable power, so renewable energy, and the power segment is also indicated by the dotted line. So what you can see is that power is not the primary energy source, and that the portion of renewable, whether on a global perspective, on a European perspective, and even in Germany, is marginal. It's in Germany 15%, and in the power segment less than 10%. I will come to this in a minute. And many people already say, well, we have reached the 50% threshold. But that's not true if you look at the primary energy. It's only true if you look to power. Yeah, natural gas, again, from a global perspective, is the fuel of the future. Here in Europe, we have a slightly different, and especially in Germany, a slightly different attitude. But in many other countries, that's the energy how to achieve climate targets. Not climate neutralities, but climate targets. In Europe, we have seen before the invasion of Russia into Ukraine that natural gas was seen as the bridge and the transition fuel into the future, replacing coal and lignite, because the power plants have higher efficiency, especially in cogeneration, where you produce power and heat at the same time, which is more effective than doing it separately. In addition, we have biomethane and biogas in Europe, and Germany is the front runner with 9,000 biogas plants from the 15,000 in Europe. So the majority of all biogas plants is here in Germany. And that's an indication how we can also produce renewable gas. But what became more and more interesting is the production of gas from power, which is called power to gas, or as you can see here in the picture on the right, the production of methane, synthetic methane, and the Dutch colleagues invented the name molectron, which means it's a molecule that stores electrons, power from wind and solar. Now, in the moment we have a new energy carrier comes on the stage, like hydrogen and biogas, the question is, what is the relation between both of them? Will hydrogen push natural gas out of the market? Is there a smooth transition or a digital switch from one or the other? And that's the question of the lecture here. Is hydrogen the new natural gas, and how can this happen? I think from these first slides, you can easily deduce the impression that climate policy will be a driver or is a driver for hydrogen because, as you all know, hydrogen, if it's burned, doesn't emit any CO2. But of course, the question is, how do we produce hydrogen? Because it's only an energy carrier. However, there's a second reason, and it's an actual reason why we should have a closer look to hydrogen. And this has to do with the global energy supply chain, and especially with the situation nowadays, these days in Germany and Europe, the dependence on Russian gas. This graph indicates just from a first glance that we in Europe get a lot of gas from Russia. And as you know, it was more than around 50% of the German gas supply. Other areas are supplied by Australia, for example, the Pacific, Japan, whereas in the last years, the US market became more or less independent due to their invention of fracking gas and horizontal drilling. So they became to a net exporting countries and will play an important role for Germany to become more and more independent from Russian gas. Yeah, the target of our government is to gain more independence from Russian coal and oil and gas. But let's start now really with the facts and figures. In this square that you can see here, you have a deeper analysis of our primary energy portfolio. The green color indicates renewable energy, yellow is gas, then brown oil, and also coal and lignite, as you can see, followed then by nuclear power. Each square stands for 100 terawatt hour. So if you count the square, roughly 6 times 6, 36 tiles, that means our primary energy demand is 3,600. No, it's a little bit less. One tile is missing. It's 3,500 terawatt hour. So just keep this number in mind, 3,500. What we try to achieve now with the new policy towards Russia is to take this amount of energy, which you can see here on the right, out of the system. 50% of the hard coal till this year, October, 35% of oil already done, and 50% of gas, which will take a little bit longer. Altogether, 1,000 terawatt hour. What we can see is that the strategy for the replacement of oil and coal is a very simple one, and I would call it a lock-in effect because we just replace one fossil fuel by another fossil fuel from the world market, which is quite liquid at the moment. For gas, it's more complicated due to the fact that we have to transport this energy in pipelines. But the approach that the German government is following at the moment is a really challenging one and a smart one. We are building new infrastructures, floating terminals, FSRUs, but they should be replaced in the future by hydrogen-ready installations. We assess as another option the import of ammonia, because ammonia is produced in Germany out of natural gas, so why not importing it directly? And we are in negotiations with other countries who deliver today LNG, liquefied natural gas, but tomorrow hydrogen. So this strategy already includes the idea of the transition. The assets we need for this are ships like the one on this slide. On the left, in the middle, you can see this floating storage and regasification unit, a ship that will stay permanently in Wilhelmshaven and other places. And on the right side, you see the tanker that delivers then the gas into this interim storage. Now, the idea is, of course, to shift this to hydrogen in the future. But let's have a quick look to the situation we are facing this winter. Some institutes have done an analysis what would happen if the European market would lose the entire Russian supply. As you can see, it contributes with 109 BCM to the energy demand of Europe. And even if we try everything that you can imagine, like taking more gas from Norway or reactivating the production in Groningen, etc., there will be a gap that remains. And it will be huge if we do not have filled our storage by the winter. And even if we will have filled our storage, there's a gap. So therefore, it's necessary to have new gas in the business, the LNG terminals, and to fill our storage till the winter. And that's the reason why it's very critical that we have seen less gas coming through Nord Stream 1 during the recent weeks. And everyone is very concerned what is going to happen after the 21st of July when the revision phase, the inspection phase of Nord Stream 1 is over, whether we will see gas or not, because this will decide how the story is going to end. But it's not really my story for today. We can talk about this more in the break, maybe afterwards, but I appreciate to give you some answers also on that. So next to the climate debate, the debate of resilience and security of the supply is a trigger for hydrogen, because the idea is not for next winter, but in the midterm, we will be more diversified, we'll have more gas and hydrogen from other places of the world, and this will increase our resilience. Now, be a little bit more radical and think more green. We have seen that things are doable if the government is really decisive and wants them, like the construction of the LNG terminals. It would take decades. In my time at Rogers, I have seen 3 trials to build an LNG terminal in Wilhelmshaven. All failed, also due to political interventions, and now it can be done in weeks. Yeah? So why can't we just speed up our energy turnaround and be renewable tomorrow? Okay, again, the tiles, the 353,500 terawatt hour. Sometimes we are very good at knowing what we don't want and not what we want. So we don't want nuclear power. Get rid of this next year. We don't want oil. That's too fossil. Okay, we replace it by synthetic oil. Coal, nobody really likes coal, even if we are dependent on this winter. But there is this debate. Maybe we can even get rid of coal before the legal frameworks demands it in the year 2038. The Green Party wants to get rid of coal in 2030. And then gas. Well, also this should be determined at least in 45. So if you add this up, there are a lot of tiles that need to be replaced. And that's not a trivial task. Maybe we can do it with renewable and with power. But again, this is where we stand. Yeah? We have at the moment 15–16% of renewable energy. And to believe that with the growth of renewable or with the abracadabra efficiency, we will achieve this target is a little bit naive. Indeed, the steps that I show you on this graph are not stair steps anymore, it's a wall we are standing in front of if you look at the remaining time. That means the only The only realistic alternative we have to achieve our climate targets is the import of climate-neutral gases. As we are now heavily dependent on import, and as Germany is a producing country that pays for its energy fees with goods that we produce here, this is the only chance that we have. Okay, maybe you are not convinced yet, so I have to deliver more arguments, and we convert now the primary energy into secondary energy and use energy. What do we do with this energy? We produce 20% power, and the rest is kept in the status of molecules. And as you can see on the right graph, only 50% of our power is renewable. That's what you can find in the press, Bild-Zeitung and other. We have already achieved 50% renewable status. Yeah, 50% of 20%, that means 10%. That's what's sometimes left out, yeah? Okay, the question is, can we speed up again and electrify Germany by feeding more wind and solar in the system? I mean, we are standing in front of the wall, but maybe a wonder will happen. But there are some reasons why this is really a mission impossible. One is, we do not have enough renewable energy here in Germany. So we cannot be self-sufficient. We have to import this energy. The country is too small. Sun is not shining often enough. Next thing is our power grid is not able to do this. We need more than 27 gigawatts new cables to be built through Germany, and that takes decades to transport the energy down to the south, like Bavaria or Baden-Württemberg. The power grid is not strong enough. We have only 80 gigawatt installed power on a reliable basis. That's the energy which is also more or less shipped through the power grid. But on a cold winter day, when all your heatings in your individual households switch on and your little burners ignite the gas, you are producing 300 gigawatt power in all the individual households. 300 gigawatt power out of the gas grid. So it's a factor 3 and more higher than any energy that you get out of the power grid. Many people don't know this at all. And finally, an important link is missing if you rely only on power. It's power storage. And here again, molecules come in the game. There is no big enough battery to store seasonal renewable power. So we need the conversion into a chemical good into molecules. This is the profile today. Our government has ambition targets to increase the share of power and renewable energy by 2030, as you can see here. That means we have to double within 7.5 years. We have to double within 7.5 years the portion of renewable power. Okay, ambitious, but assume it can happen. There is still enough surface in this square that asked for an answer. There remains the need for a complementary decarbonization strategy for the remaining demand. And that's hydrogen. There are different options how to produce hydrogen and also biogas, which I count now as hydrogen, because if you stop the process of digestion, you can also produce hydrogen through the same processes. Here in Germany, we have a potential of 100 terawatt hour, one tile again. But with some tricks, we can make 3 tiles of them, 300 terawatt hours. Yeah? The government claims that they will have a rapid transition towards power to gas, 40 gigawatt power to gas. 40 gigawatt power to gas delivers approximately 1% of our primary energy. So even these gigantic ideas and processes and projects to have 40 gigawatts of electrolyzers here in Germany is nothing. Pyrolysis is a very interesting technology where you crack methane without emissions of CO2, but just carbon is released, black carbon which the industry can use. Very promising technology, 8 times more efficient than an electrolyzer. And we have some projects with BASF in this field, very promising. But for the short term, imports are important. Imports from all over the world, which have already been initiated by our previous government. So I skipped this slide about the pyrolysis, which shows how pyrolysis plants could be interconnected with the chemical industry, where you can also supply out of such a plant hydrogen for the industry, for power plants, and for domestic supply. Please have a look afterwards. The global sourcing of hydrogen has to start now, and as you will see from the context as Mr. Habeck had, to the United Arab Emirates or to Australia and US, this is the idea that we just diversify our sources and get this energy carrier from Australia, from the US, and maybe also from North America and other places. The agreements and MOUs have been already signed last year. What we need now are real projects with significant amount of energy. Okay, this is the holistic idea of hydrogen. And as a physicist or scientist, there are three questions that need to be answered if you think about hydrogen, namely, is there enough for us? Is it limited? How do we transport this energy? And what is with the end appliances? So, will we have enough hydrogen? Which infrastructure is the suitable one? And at the end, will the devices also operate as we know this, for example, from natural gas? I would like to start with the first question, because maybe you know that many people say, hydrogen, that's the champagne of the energy turnaround. We can only use it for steel and no one else is allowed to get it. Well, what do we have to replace is the 1,000 terawatt natural gas or the remaining area of the square that I showed you, which is even larger, namely nearly 2,000 terawatt hours. Okay, let's collect what we have. LNG is coming in the next years and decades, and it will be replaced by ammonia or hydrogen. We have biomethane with a potential up to 300 terawatt hour, and now hydrogen. Hydrogen on the short and on the long term, green hydrogen, blue hydrogen, turquoise hydrogen, which I will explain in a minute. The results that you can see here have been done by a study, or the results are the results of a study of Frontier Economics together with DVGW. So if we add all these contributions up, we can easily prove that we can supply 1,000 terawatt hour and therefore replace the whole natural gas market by hydrogen only. And this was a conservative estimate. We have also an optimistic case, and the optimistic case covers the whole end use of Germany with hydrogen. The assumptions of the different cases are described here. As you can see, we start, of course, also with gas and hydrogen from Germany, electrolyzers, but then we go to our neighbor countries which have better conditions, more sun or more wind or more biogas, even Ukraine, for example. And we have the assumption that 3% of the renewable power in these countries is converted to hydrogen, only 3%, and Germany gets 15% of this. So a little contribution, but if we just collect this from the EU, from MENA countries and from Norway, we can achieve the 1,000 terawatt hour or the 2,000 terawatt hour. Other studies issued last year for Europe prove the same. Germany is approximately 1/4 of the European energy demand. So that's, for me, always a rule of thumb. 1/4 of the energy goes to Germany. And here you can see on the left side that Guidehouse investigated last year that 4,000 terawatt hours could be harvested in Europe, and 1/4 of this is 1,000, exactly what we need. And on the right side, you see a study from Hydrogen for Europe with a different composition of blue and green hydrogen, but with the same number, they end up at 100 million ton. And that's exactly, again, 4,000 terawatt hours. So we are very confident that we can really supply all interested customers. A word to the different colors, gray, turquoise, green, hydrogen. The only interesting thing is not the color, but the carbon footprint. And if you produce hydrogen from wind or solar energy, you can have a carbon footprint of 10 CO2 gram per kilowatt hour compared to natural gas, which is around 200, 230. If you produce turquoise hydrogen from pyrolysis, you are very close to the one from wind energy, and the blue hydrogen state of the art is higher, around 100, but our future prediction is it will lower to 40. We have done more detailed studies on this, but I just picked this picture. So there is no reason to discriminate any kind of hydrogen as long as it is better than natural gas, because that's the step on the pathway to Paris towards climate neutrality. Now let's turn to the more specific or difficult question, what about the infrastructure? Well, of course, the idea was to use the natural gas infrastructure. We therefore decided to study all the materials. As a standard setting body, we have to approve afterwards whether a steel pipeline or a plastic pipeline can be operated with hydrogen or not. And we did this together with MPR and TÜV and found there are no limitations in Germany to use the existing grid for the supply of hydrogen. This has been proved by long accelerated live testing, and the general result is that the existing asset is still able to operate for a whole generation again, based then on hydrogen. We also have to do analysis on every component which is part of the grid, like meters, safety devices, etc. Even permeation was studied. Here we have a more dedicated picture where we know which component need to be replaced and which not. And here are some examples. Whenever you burn natural gas and try to switch to hydrogen, there is a certain limit where you have to exchange the component, for example, the turbines and compressor stations. But you either replace them by an electric drive, or you buy your new turbine from Siemens, because Siemens offer everything from 0 to 100% hydrogen. Also, the meters here in these pictures are hydrogen ready, other devices not. This knowledge has been gathered in a compendium and will be issued next year in a data bank, so that any grid operator can connect with his asset data bank to our data bank and compare whether there is any component in his grid that need to be exchanged. The question is, at what cost does that come if you have to exchange some components? And here also some estimates that we will have to pay around 7 billion euros if we want to shift the distribution grid to be hydrogen ready, and a little bit more, 45 billion euros if the entire gas grid is 100% hydrogen ready. There it's more expensive because in the big transmission pipelines you have these more expensive turbines which need to be replaced. Yeah, another study from Gas for Climate converted these costs in an additional fee on top of the product costs, and the result is 1 cent per kilowatt hour for hydrogen for transport through the whole of Europe. And as a rule of thumb from doctor thesis, I have here also this indication that their conversion is approximately 10 to 15% of new build cost. Now, these are big numbers, but if you think that 30 billion are spent a year in our energy turnaround, and that we have probably already spent 100 billion euros in the energy turnaround for windmills and solar panel to replace 10% of our energy by renewable energy, then this is super cheap and should be done. Yeah, this is another myth I would like to mention. People say, well, hydrogen has only 1/3 of the energy content of natural gas, so we lose all the capacities in the pipeline grid. They are not big enough anymore. That's wrong. Hydrogen travels faster than natural gas, and it's also just easy to understand that we have the same transport capacity in the pipeline because the Wobbe index is the parameter that determines the pipeline capacity. And that doesn't change whether you have 0 or 100% hydrogen in the grid, as you can see from the left curve. So the big transmission lines keep their capacity. Now let's look at the end device. There are a lot of end devices, so I picked only some of them. One is the production of heat, district heating. And here our proposal is to go from coal-powered CHPs for district heating to natural gas and installations which are hydrogen ready in order to be able to do the next step for total emission reduction. Again, you see here the emission reductions in terms of grams per kilowatt hour in the clouds and on the picture. And this seems for us a doable way. And there are some smart companies which announced a couple of days ago, EnBW in Baden-Württemberg, that they will exactly do this, the fuel switch towards natural gas with the perspective to go into hydrogen on 3 of their coal-based power plants. Hamburg-Bergedorf is an example where CHP unit has been installed already 2 years ago and which is supplied by 30% hydrogen admixed to natural gas to heat up the lodge area here in Hamburg without any problem. And suppliers like 2G offer engines which are total flexible from 0 or 100% natural gas or hydrogen. So this is also an innovative technology already available. The real critical thing are the 40 million households in Germany. Half of them are heated by natural gas. And as you can see from the pie chart on the right, the energy efficiency standard in Germany is quite poor. A lot of installations need to be replaced, and also the house itself loses a lot of energy. Well, with hydrogen, we are connected to half of the households. So if we deliver, instead of natural gas, hydrogen, step by step, then this is an offer how to decarbonize also your private demand. The existing burners in your household can operate with 20, 30 or 40% hydrogen without any change. But above this, you have to exchange the heater, but new devices are ready. 100% hydrogen ready from next year onwards, and 2 years later, this will be the European norm. The advantage is that you can do this without renovating your house, because the energy carrier is just strong enough to deliver any heat that you need compared to an electric heat pump. The tests that we did are shown here in the graphs on the top. I will not explain further details. More interesting is that we did a big field test in Schopsdorf near to Berlin with around 400 customers without changing their old devices at all, just supplying 20% of hydrogen to their homes. This has been done in Germany, but also in UK in the project High Deploy with even more samples. And as I said before, next year we will have very flexible devices in the market between 20 and 100% certified for hydrogen, and the standard, European standard, will then that be up 20 from 25 onwards, that all gas burners are hydrogen ready. This is an example from Fissmann, a company that is very dedicated to change every device that they have in the different power classes to hydrogen. And we are not alone with this. It's not a German idea. There are many projects in the heating sector down to the end consumer driven by the European Heating Association, as you can see from this map. To be clear, it is obvious if you look in the developments in the different municipalities and countries that more and more houses will be electrified, and more houses, especially new build, will use electricity and electric heat pump. However, there are some restrictions. First restriction is that we see the gap we are approaching. If we step out of coal and nuclear, we lose power, while the demand through e-mobility and electric heating is increasing. And this endangers the stability of our power grid. The gap might be up to 100 gigawatt. The next challenge is that we have to build new transmission lines. I mentioned in the figures before the 27 gigawatts from north to south. And finally, this will have consequences for the power price. Our predictions, which are in line with those of others, clearly indicate that we will have a dramatic increase in power price. And in this number that you find here on the slides, the price, the fees, the tariffs coming from the additional infrastructure have not been even taken into account. So those who are betting now on electric heat pumps might see a big bill in the future. The other reason why we have to be careful with our electric heat pump strategy only while a technology mix is better than just relying on one technology, is that it will not work. It will not work under the current conditions where we have low restoration rates. 1% of the households are renewed per the installation per year. So all studies predict that we have to increase this up to 2 or 3%, which is enormous. Then we lack qualified staff which are able to install electric heat pumps, and it might be very costly depending on the house, whether you have already installation or not. So that can easily exceed 100,000 euros. With gas as a solution, we can keep up the normal restoration rates. For an installer, it's not a problem. A gas burner operates in the same way like a hydrogen burner, no change at all for them. And also price-wise, there is no change. And the devices can be delivered for 10,000 euros. Remember, you do not have to change your house. You can do this if you want. If you are environmental aware and want to lower your energy bill, of course, you can do it the years later, but you are not forced to do it immediately at the same time when you decide to have this new heater in your house. Another reason why we should think about the use of this technology is we have invested a lot of money into this, and these investment costs should also be returned to the companies. So we should reward German entrepreneurship in this area. If we want to sell these devices to the world market, it makes sense to apply them also in the home market. And we therefore say that an early installation of a hydrogen burner should be rewarded, and also that the change profile of natural gas over the next decade should be taken into account as a contribution to climate reduction. Yeah, well, from my perspective, I can make 3 ticks on the 3 critical questions. Do we have enough hydrogen? Does the infrastructure work with hydrogen? And is it possible to maintain or to change the devices? The real challenge is now to synchronize these processes of the ramp-up of the hydrogen, also the change in the grids. We have a big project called H2 vor Ort with all the DSOs in Germany, and they have to deliver plans to us how they will split their grid into a natural gas, into a hydrogen grid, or an admixture grid, or where they will inject biogas, so that we can develop this implementation plan. And of course, their existing devices in the households have to be renewed until 2045. This whole strategy comes with a lot of benefits. It's not only the energy triangle I'm talking about with the security of supply or affordability of energy or with decarbonization, as you can see on the left side, these attributes. It's also additional economic benefits like the secure of workplaces, less constructions in cities because you can use the existing infrastructure, income for municipalities who can operate and who can give licenses to energy companies to operate these assets. And at the end, competitive prices and an interesting portfolio of energy. Just think about Tesla and the decision to go to Berlin, or Intel and the decision to go to the east of Germany. It's because there is the appropriate energy mix available. And in the future, it will not be only renewable power or water, it will be also hydrogen, access to hydrogen. My last minutes I would like to spend with my recommendations, what need to be done. At the moment, the most urgent thing is we have to keep the energy prices down, whatever it takes. Because there's a storm developing in this class, and the whole energy market is really heated up in an irrational way. That means we have at the moment, we have to maximize deliveries of natural gas from Norway. We have to foster the connection of the FSRU. From my connections, I can tell you that by January next year, they will be connected to the German pipeline grid, and the pipelines will be built. We have to improve the European interconnectivity so that we can shift more gases from east to west and the other way around. Maybe we will see a debate about the reactivation of the Groningen field. We need clearer signals to the market, to the energy market, for example, that protected clients are protected, whatever is going to happen, whether we will see Nord Stream gas or not. Yeah, and of course it makes also sense to save energy. That is never wrong. What we demand from the politics is a clear commitment to the gas bridge, because this will lead us to hydrogen. There is no other way to get there. The industry needs clear investment schemes. That means a realistic payback times, 20 years for an investment. You cannot change the strategy after a couple of years and then say, well, invest please in coal, and 5 years later it's gas, and 5 years later it's renewable. We need this long-term investment. And now we need this for power plants, gas power plants that are hydrogen ready for the next phase. As everything is going to be more expensive in Germany, I think every one of you has their own experience. We will see a debate where we'll talk about the best climate investment. Where is €1 be best spent to save CO2? And this can be also an investment into gas and hydrogen, not renewables only. What we need is a governmental support for large-scale imports, especially better contacts to Norway. They are ready to deliver hydrogen. They have experience with CCS technology. They are ready to go. It would help if we would have a clear target, as we had for power, also for gas, that the carbon footprint need to be lower and lower over the years, so that the industry can always align to this downsizing path. We need a joint regulation between natural gas and hydrogen. It's absolutely irrational to split operators into those who operate a hydrogen grid and a natural gas grid. How can any transition happen then if you sort them in this way? But this is currently debated in Europe. We need the acceptance of the hydrogen ramp up as a contribution to our climate target. And last but not least, we cannot make the calculation without the customers. The customer needs an incentive if he decides to buy a hydrogen-ready burner, or if he decides to buy biogas or a hydrogen mixture now to make this market lift off. Well, will hydrogen be the new climate-neutral natural gas? My answer is a clear yes, and it's time to switch now. Thank you.